So we previously looked at the addition to an internal alkyne. And for internal alkynes, the carbons that are part of the triple bond are both secondary. But what happens if one carbon is secondary and the other is primary? Well, we already know that when we dealt with an alkene, the acid catalyzed hydration made the more substituted alcohol. Well, it turns out that the same thing will make the more substituted alcohol if we have different substitution of the carbons that have the pi bonds for an alkyne, meaning that we have a terminal alkyne. However, the reagents will change slightly. We need an additional catalyst called mercury sulfate. And the mechanism of this reaction will be slightly different than the mechanism in the absence of mercury sulfate. So this is the mechanism or the reagents for the acid catalyzed hydration of a terminal alkyne, water, H2SO4, and HgSO4. This will produce as the first intermediate the enol, and the enol will tautomerize to the ketone. And the takeaway is that the more substituted carbon, the secondary carbon, in the final product will be the carbon that has a C double bond O. So the orange carbon in the reactant is secondary, it's more substituted. So in the product, that is the orange carbon that has a C double bond O. And what happens to the primary carbon is that it gains 2 hydrogens. So we can write it out. Secondary C gains C double bond O. Primary C gains 2 times C to H bond. So it gains 2 hydrogens. Perhaps we should just say 2 hydrogens. Okay. So again, because the terminal alkyne is less reactive, the rate of the reaction is increased when we add a mercury ion catalyst. So the mechanism for catalysis by mercury sulfate will completely dissolve to mercury and sulfate ion. The mercury cation, Hg2+, will add to the pi bond, creating a 3-membered ring. Water will then add to the more substituted carbon. So we create the 3-membered ring here. Water adds to the more substituted carbon, breaking the 3-membered ring so that the electrons go to the mercury. This creates a protonated alcohol, mercury intermediate. Notice the charge on mercury changed when the electrons were donated from this bond. A second molecule of water will deprotonate the protonated alcohol group. So subtract this hydrogen using the electrons from water. That creates hydronium ion, and these bonding pair between the oxygen and the H go to the oxygen and the positive charge is eliminated. So that we have the alcohol group, and then we still have this mercury Hg plus attached at the less substituted carbon. So this is a mercuric enol. At this point, we tautomerized the mercuric ketone. We this pi electrons gain a hydrogen from water. Mercury will spontaneously dissociate to Hg2+, so the bonding electrons from carbonate mercury break. They go over to make a double bond between the carbonyl carbon and the CH2 carbon. And the pi electrons from carbon and oxygen gain a hydrogen from water. So this produces the enol, water and mercury ion. And since we are an acid, this enol will tautomerize to the corresponding ketone. And the ultimate is that the more substituted carbon ends with having a double bond to oxygen. Okay. Now, hydroboration oxidation for an alkene. So for an alkene, these reagents cause the alkene to become the less substituted alcohol. Okay, if we have an internal alkyne, but only when our carbons were, when one carbon was more substituted than the other, right? So for an internal alkyne, they are both secondary, so there is no more substituted carbon. And so what we end up with hydroboration oxidation is that we end up adding an OH group. And I'm not going to go through the whole mechanism, guys. No. Notice that they use the R2BH instead of the BH3 because that's shorter. We don't have to replace all of the H's with R groups. And then the THF, and then, you know, you add hydrogen and the boron groups in, and then alcohol replaces the boron. And so it creates, it always makes the trans alkene if you only add one OH group. But in the end, the trans substitution doesn't matter because it tautomerizes to the ketone, which doesn't have cis or trans identity. But the point is that this is a symmetric alkyne. Internal alkyne equals equally substituted carbons, so there is no more substituted carbon. So what we end up with is a ketone because there is no less substituted carbon for the hydroxyl group to bond to. But what if we did have a more and a less substituted carbon? We know that boron is an electrophile. This is our preferred four-odd reagent because it requires a 1-to-1 ratio instead of a 1-to-3 ratio. Okay, and then what occurs if we have a terminal alkyne This is when we have a more substituted and a less substituted carbon. So we have secondary and primary. Well, that's where you remember that hydroboration oxidation forms the less substituted alcohol for the alkene. So oxygen adds to primary carbon. So in this case, we're going to take our primary carbon, and in the final product, we're going to add C double bond O at the primary carbon. And this means that instead of forming a ketone, we form an aldehyde. So hydroboration oxidation for a terminal alkyne forms an aldehyde, and acid catalyzed hydration for a terminal alkyne, acid catalyzed hydration, terminal alkyne, forms a ketone. So the secondary carbon gets the carbonyl group when we have mercury and HgSO4, and the primary carbon gets the C double bond O when we have hydroboration oxidation. Hydrogenation of the alkene. Hydrogenation of the alkene, H2PDC, gave us the corresponding alkane as a final product. This reagent has the exact same effect on a triple bond. We go from the corresponding alkyne and we add hydrogen to each of the pi carbons until we become an alkane. And with this reagent, it is not possible to stop at the alkene. So we cannot stop. Even if we used half of an equivalent so that there's twice as much alkyne to H2PDC, the reagents would still carry the reaction all the way to the alkane. When we use hydrogen over palladium and carbon. But what if we want to make the alkene using hydrogenation? Then we would have to use a different reagent. And this is called Lindsay's Catalyst. Lindsay's Catalyst is a poison catalyst, that's what we call it. And what you're trying to do is to make the reaction less efficient. So you're poisoning it to make it weaker. Make it weaker so that it stops at the alkene. The most common catalyst for Lindsay's Catalyst is lead sulfate. Instead of palladium over carbon, we use lead sulfate. So this lead sulfate makes it harder to add hydrogen to the double bond. So that when hydrogen adds, only one equivalent of H2 adds and we produce the alkene. When we are adding hydrogen gas, you have to remember that a molecule of H2, both hydrogens add at same time, so they add syn. Now, if the double bond is at the end of the molecule, that won't matter. So if it's a terminal alkene, the addition of the hydrogens syn won't matter. But what happens if it's an internal alkene? And we add the hydrogens through syn addition using H2 and Lindsay Catalyst. We produce the cis alkene, and the reaction is stereoselective. So H2 Lindsay Catalyst only produces the cis alkene for an internal triple bond. Starting with an internal triple bond, we only produce the cis alkene as our product. Oh, okay. I'm going to erase then. So here's their little spaceship mechanism, that's what I like to call it. So you have your catalyst, your lead sulfate. It still immobilizes the hydrogen for the pi bond to add it, but it doesn't do it as efficiently. And so we can only add H2 to one pi bond. Okay. So we can make the cis alkene from an alkyne. Well, guess what? We also want to be able to make the trans alkene from an alkyne. And this is going to be our first radical reaction where we have one electron transfer. The anti-addition of hydrogen to a triple bond creates the trans alkene, and the reagents to create the trans alkene are sodium or lithium metal in liquid ammonia. So these are the solid, and this reagent is very similar to something that we're going to use later. So later you're going to see in different reagent sodium amide. And so you have to note that NaNH2 is not equal to sodium solid with liquid NH3. These are not the same thing. They're not the same thing. And we're going to use the NaNH2 later in this PowerPoint. So be sure you understand what each of them is going to do when you take the test. Okay, so if you see solid sodium or solid lithium with liquid ammonia at -78 degrees, that reaction with an alkyne produces the trans alkene, or the alkene where the hydrogens add anti. Okay, and now we need to look at the mechanism. Note that these are all half arrows. Half arrows equal 1 electron transfer. Okay? So in a half arrow, you only have half of the arrowhead, and that's what we're referring to. Let's look at this mechanism. Sodium metal is unstable. It does not have an octet in its outermost shell. So sodium metal likes to give up electrons, specifically one electron because it's a group 1 metal. So sodium metal has the Lewis structure of Na dot, 1 electron dot. Then 1 electron from sodium is donated to the pi carbon. In reaction to that, half of the pi electrons combine with the donated electron to generate a lone pair on the carbon, and the other half of the pi bond goes into a radical on the other sp2 carbon. So we have a radical anion, 1 carbon with a lone pair that's negative and 1 carbon with a radical electron. The negatively charged carbon donates its new electron pair to make a bond to hydrogen, producing an amide ion, NH2-. The radical carbon electron combines with another donated 1 electron from sodium. Sodium goes into the cation state, giving up its electron completely, not forming a bond, but just giving it away. And we create another negatively charged lone pair on this carbon. So now we have a negative carbon. This negative carbon will then take a hydrogen from NH3, producing amide ion. So ultimately, this reaction produces 2 equivalents of sodium cation and 2 equivalents of amide anion and our trans alkene. Why does this reaction occur by trans? The lone pair and the radical electron repel each other, and so they must be on opposite sides of the molecule, anti to one another. The result of the lone pair and the radical being anti gives anti-addition of the 2 hydrogen atoms. When we get to the position where we have 1 lone pair and a hydrogen added, and we don't have electron repulsion anymore, what prevents rotation so that the second electron, so the second hydrogen doesn't add syn, is the steric strain that would occur between the 2 R groups on the vinyl carbon, so that the trans is the more stable final product because it doesn't have the steric strain of the cis product.